Okay, so we're going to learn more about differentiation, this time in the context of inverse functions. So first thing we're going to do is to look at a pretty simple pair of inverse functions. We have the squaring function, y equals x squared, and then also the opposite, the inverse function, right, the square root function. And this is the standard notation f and f inverse. We're going to take x positive just for the purpose of illustration, just to make things easy. Okay. Alright, so you might remember some graphical relationships here between a function and its inverse. So you can see the parabola down here, y equals x squared, the positive half, and then also the inverse function, y equals square root of x. And what I have done here in this diagram is to highlight the corresponding points. So you can tell with inverse functions, the x and the y coordinates are playing opposite roles. So on the parabola, we have this point here, 3, 9. And that makes sense because when you square 3, you get 9. And the opposite happens with the square root. So we have the point 9, 3, right? The square root of 9 is equal to 3. So this little bit of calculus is all about how the tangent lines, right, are connected when you talk about a function and its inverse. So I'm going to put the tangent line in here so we can see the slope. Right, so you can see this one here, nice and steep in that first picture. And then this one here, pretty much the opposite, right? Fairly flat when you look at that one. Okay, so you can almost predict the connection here between the slope on the function and also the slope on the inverse. But what we're going to do with this exercise is to try to make that precise. Okay, so we're going to go through the work here. I'm going to make a couple of columns here to illustrate this point. And we're going to focus on the point 3, 9 and also 9, 3. So when you think of this function, y equals x squared, it's pretty simple to find its slope. So f prime here is equal to 2x by the power rule. And if you want the slope of the parabola at the point x equals 3, then you simply insert 3 in for x. So this will be 2 times 3, or 6. So this little calculation is just telling us the slope of this steep line that we see here at the point 3, 9, m is equal to 6. So now what we can do is to try to do the opposite here, right? Or to try to do the same basic thing to find the slope of this tangent line. This is now the inverse function. So our notation here, f inverse. And this we know is the square root function. So now we have to differentiate this. So when we find the derivative, it's a nice idea to use parentheses here because the notation is complex. So it is the slope of the inverse function. And so this will be x to the 1/2, so just 1/2 x to the negative 1/2. And then you can rewrite that in this manner here. So this is the formula that you can use to calculate this slope, and we're going to calculate it when x is equal to 9. So if I extend this here, if you want the slope of the inverse when x is equal to 9, you simply insert 9 right here. And I think you could see this, right? Square root 9 is 3, and then you double that. So the slope you end up with here is 1/6. So that's the big connection to make, because what happened here is not a coincidence. You can see this slope is a steep one, and that has m equals 6, and this one here is not steep at all, and m is equal to 1/6. But the bigger connection here between the slope of a function and the slope of its inverse at the corresponding point is that these numbers are reciprocals. And in fact, that is where this notation comes from, right? F to the power of -1. So we should take a minute just to formalize this, because there is a result. And this is typically the way you'll find this written in calculus books. Okay? So it says here, suppose we have a point on a function. So let the point AB be a point that's on the graph of y equals f of x. So naturally we have to assume that f is going to have an inverse, and then also that that inverse has a derivative. But this is the meat of the statement here, that if you want to calculate the slope, right, the derivative of the inverse at a point, then the quickest way to do it is to calculate the regular derivative of the function at that same corresponding point and to take the reciprocal. So you can see the dynamic here that the inverse is calculated at b, right, but the slope of the original function occurs at a. And you could see that in the previous example. Okay, so for the rest of the lesson here, I'm just going to talk about inverse trig functions, and I guess we'll just discuss a couple of them. So I'm going to start off with the one that probably comes to mind, right? You can think of the sine function, right? Y equals the sine of x. So the inverse of this function, this is the arc sine function. So often written this way, and you might also find it expressed in this manner. So either one of these here. So the question that we're going to ask here in this little derivation is just a simple one, right? So if we have an inverse trig function, y equals the arc sine of x, how do we calculate, or how do we find dy dx? All right. So there is a way that we can go about and to go through and to do this. So we'll remember that if you start off with an original function, if you want to get its inverse, then we're going to change the roles, or interchange the roles of x and y. Right? So x and y are going to play opposite roles. So if you want a way to express the arc sine function, we could, instead of writing y equals the sine of x, we can write x equals the sine of y. So this is what I'll go through and do. Right, so we could write this in this way here. Just the sine of y is equal to x. Right? So this is equivalent to talking about the arc sine function, right? As long as we're within the proper domain and range, right, for x and y. So if you want to find the derivative here, we're going to differentiate implicitly. We learned this in an earlier lesson. So we're going to take both sides and differentiate with respect to x. So the sine function is going to give us the cosine function, and then we use the chain rule. We're going to get a dy dx out of this, and then the derivative of x is pretty simple. We just get a 1, and then we solve for dy dx. So the derivative here comes really quickly. So it's 1 over the cosine of y. But if we're starting off with the arc sine function, right, just going back to this idea here, we have y as a function of x, and we often want to express the derivative also as a function of x. So what we have at this point is we have it in terms of y, but we should be able to go through and solve for x. So now if we look at this statement here, the sine of y is equal to x. This is the tricky part of the work. So we're now going to treat y like an angle and think about our triangle trigonometry. So we're going to draw a right triangle, and y here is our acute angle. So the sine of y is equal to x, and so we remember sine as being opposite over hypotenuse. Okay, so the sine here is going to be x over the 1, right? Opposite side, hypotenuse. And so once you have two sides of the right triangle, you can use the Pythagorean Theorem to get the other side. So if you solve for the base here, you get the square root 1 minus x to the power of 2. So the advantage of having this triangle is we can now look at this triangle and actually read this directly off of it. Right? The cosine of y is the adjacent side over the hypotenuse. So if you look at this triangle, again treating this as an angle, we're going to take the adjacent side and then over the hypotenuse, and that will be our cosine. So to finish up this formula here, this is going to be 1 divided by the cosine. And the cosine will just be this square root piece here. Okay, so there's a lot of stuff going on here. And this is telling us that if we have the arc sine function, so if we go back to this question here, we have y is equaling the arc sine function. What is dy dx? It turns out to be a rational function, not a trig function. So 1 divided by the square root, 1 minus x squared. So this is basically what we just came up with. This is the important result in compact form. If y is the arc sine function, here is the derivative, 1 divided by the square root, 1 minus x squared. So a good thing to keep in mind is that all of these rules have chain rule versions, so it doesn't hurt to write those down. So if you have y equals the arc sine of u of x, right? So the arc sine of u, where u is some function of x, then that means you can use the chain rule on this. So dy dx, no surprise, is going to have the same form as this. So it's going to look like 1 over the square root, 1 minus u squared, right? No matter how complex u is. But remember, the chain rule says now differentiate the function u. So we're going to multiply this by du dx. So the big thing to notice is that in this case, right, if u happens to be just the function x, then this formula here becomes this one. Alright, so I'll just do one more here. We'll think of the arctangent function. And I'll go through this one a little bit quicker because we went through the arc sine. So we're going to think about the arctangent function and say, what does y prime look like in that case? So here we go. We can think of y equals the tangent of x, but instead we're going to think of the inverse function. So we're going to begin work with this, right? The tangent of y is equal to x. So if you want to, you could already sketch a right triangle directly from this, because that will lead you to what you need. We're going to treat y just like it's an angle. So I'll just do that to start. It's not going to hurt. Okay, and the tangent of y, this is the opposite over the adjacent side. So we're going to get x. So we have opposite over adjacent. So notice again, this picture is just a diagram that indicates this statement. The tangent of y is equal to x over 1. And then you can get the hypotenuse here by the Pythagorean Theorem. So this will just be 1 plus x squared, but it's underneath a root. Okay, so we begin and finish exactly like the last problem. So differentiate both sides with respect to x. So the tangent is going to give us secant squared of y, and then we have the chain rule, dy dx. And then the right hand side, nice and simple, you get a 1, and then just divide by secant squared. So you could write 1 divided by secant squared, or you could simplify things and just write cosine squared of y. So this again is pretty much the answer for the derivative of the arctan, but we would want to express this back in terms of x, and we can do that by looking at this diagram. So we can see in the diagram, as long as we can read off the cosine of y, we're all set. And the cosine of y, if you look at the diagram, is the adjacent over the hypotenuse, right? So it's going to be 1 divided by the square root of 1 plus x squared, and all of that will be raised to the second power. Okay, so I'll see if I can fit all of this here. So y prime is going to equal 1 over the square root, 1 plus x squared. Okay, but it's cosine squared, so all of this will be squared. And so that does nice things with the square root. So y prime is just this. And so just like the arc sine function, it's not a trig function that you get for a derivative, but rather a rational function. So this is the relationship that we can see here. So we have all the work to support it. So if you have the inverse tangent or the arctangent function, this is what dy dx looks like, right? And you can see it in the derivation. Okay. And one last thing, we'll just write down the chain rule variation of this. So if you have y equals the arctangent of u of x, right? So not x, but a more complicated version here, then you guessed it, the derivative is going to use the chain rule. Okay, so dy dx is going to have the identical form here. It's going to be 1 over 1 plus u squared. Has that same form, and then you multiply by du dx. So a shorthand here that sometimes people use, instead of du dx you can just write u prime, and you can express it in this form. So 1 plus u squared, and then u prime upstairs, right? This is the same version as that. And again, just like the earlier comment, in the case that u happens to be x, this formula here becomes that one.